Okay, this is 9.2, combining two functions, so sums and differences. So we're looking at the addition and the subtraction of two functions. Our goal is to represent the sums and differences of two functions graphically and algebraically and determine their properties. Luke, can you read that little blurb, please?
The sound produced when a person strums a guitar chord represents the combination of sounds made by several different strings. The sound made by each string can be represented by a sine function. The period of each function is based on the frequency of the sound, whereas the loudness of the individual sounds varies and is related to the amplitude of each function. These sine functions are literally added together to produce the desired sound. The sound of a G chord played on a 6-string acoustic guitar can be approximated by the following combination of sine functions. Y equals 16 sine 109x plus 9 sine 392x plus 4 sine 784x.
Okay, when functions are added or subtracted, how do the resulting characteristics of the new function compare with those of the original function? So to explore this, we explore a similar but simpler combination of sine functions by examining the properties of the sum defined by.
Morning, Mr. Mio.
Hi there.
Could you please tell your paper?
Yes. Examining the properties of the sum. Copy and complete the table of values and use your results and the graph shown. No sketch. The graph the y equals sine x plus sine 2x, where x is between 0 and 2 pi. So this is our sine x graph. We know all these values, or we should know all these values, and the same goes for our sine 2x values. Okay, just going to substitute this value in x over here in the function for x here. So sine 0 is, as we know, is 0. Sine 2 times 0 is also 0. Sine pi over 4 is 1 over root 2, or 0.7071. Okay, we do the same thing here. We're just going to multiply this by 2, so that becomes 90, so sine 90 is 1. Okay, so all these values should be straightforward enough. Next thing we do is to find this value, this plus this, we just add these up. Okay, so this would be just adding these two values. Okay, so we're just adding those values up. So now we have x values and y values of this function, right? Okay, so we can just use like a table of values here to graph this now. Okay? So if we do that, our function looks like this. Okay, this is 2, negative 2, this is negative 1, and this is 1. So remember, when I calculated those values, my highest points were 1.7, my lowest points were negative 1.7, so those are these points here, right? So this is what our graph looks like. We can see here, again, this is only graphed over the range of 2 pi. Okay, so we can see here that we have a period that's starting to repeat itself at this point here. Okay, any questions so far? How I came up with this graph? This is any questions? How that was created? Pretty straightforward. Okay. B says, set the calculator to radian mode, adjust the window settings, and graph. Verify your graph in part A by graphing y equals sine x plus 2x. So that was what I just showed. Okay, there's your graph. And you'd get that if you use a graphing calculator. What is the period of y equals sine x plus 2x? How does it compare with the periods of y equals sine x and y equals sine 2x? All right. Well, to compare them, first we need to know what is the period of y equals sine x. What's the period of sine x? Nobody? Sine x, right? 2 pi, right? Good. Sorry, this graph, this is my bad here. This was 4 pi. This was a graph, for some reason they graphed two periods. This is 2 pi. Okay? And we know that. I think I graphed it here as well. Yeah, so this is a little bit better. So remember, in radians, pi is what? What's the value of pi? 3.14. So there's 1 pi right here. So here's 2 pi. That's 6.2. So that is 1 period right there. Okay? So what we notice then, to answer this question, what is the period of y equals sine x plus 2x? What's the period? What did we just say? 2 pi, right? How does it compare with the periods of y equals sine x and y equals sine 2x? Well, it's the same as this. And what's the period for this? What's the period for this? Oh, you guys forgot a lot, eh, over the holidays?
Oh, yeah.
That's right? Pi. Thanks, Alex. Yeah, it's pi. Because we divide the 2 pi by k, right? In this case, k is 2, okay? So the period is pi there. So how does it compare? Well, it's the same as this function, and it's double this function, okay? So the whole purpose of this is we're trying to establish a pattern, right? For combination of functions. So that's duly noted. What is the amplitude of y equals sine x plus 2x? How does it compare with the amplitudes of y equals sine x and y equals 2x? So what was the amplitude of this? I'll go back to this page here. Who can tell me now? What is the amplitude? So you can see it in two variations. You can see it in the graph, you can see it in the table. The amplitude, yeah? Right, so the amplitude of this (1.701). Okay? How does it compare with y equals sine x? What is the amplitude of y equals sine x? Somebody said it? Yeah, what was it? 1. Good, thanks, Luke. So this amplitude is equal to 1. And what's the amplitude of this one? Come on, guys. Amplitude of sine 2x. Yeah. 2? What? No, 1. 1. Amplitude is this value, right? Right in front there. It's 1. Yeah. A lot of you guys are a little rusty. All right. So far, not much of a pattern, right? We can see that our new function has the same amplitude of both the old functions, but its period is the same as one of them, but double the other. Okay? So not kind of no defining evidence yet to a pattern. E says create a new table of values and use your results of the graphs of y equals sine x and y equals sine 2x to sketch the graph. So this time now we're subtracting them. Sine x minus sine 2x. Okay? Repeats B and D using this difference. So we're going to go through that same process, but this time by subtraction. So we get our same table of values, those same values, but this time now we minus them. Okay, so we come up with our y values for our new function. Okay? We graph it and it now looks like this. Okay? So we can see the period is what? What's the period? Yeah, thank you. 2 pi. Okay, and the amplitude looks like okay. So there's our function, and here it is again. Okay. So F. So we're supposed to repeat all of them. So we did that. We looked at the period. So the period is the same as 1, but it's double another. The amplitude is above 1, but sorry, above both of them. So the exact same results. F. Do you think that the graph of y equals sine 2x minus sine x will be the same as the graph you created in part E? Explain. Check your conjecture by using graphing technology to graph this function. So F. So they're asking, do you think this will be the same as this? What do you guys, Joseph, what do you think? No. Okay, I agree with him. Why? Yeah.
Because now it's negative sine x, not negative sine 2x.
Yeah, so the signs have changed, right? But just like we know with kind of just simple math, right? 3 minus 5 is not the same as 5 minus 3, right? Actually give us different values. So using that conjecture, I would say that this should give us different results because, you know, the opposite function is now flipped or negative, so as they combine, it's going to be different. Okay? Remember, you can always use this sort of analogy as well, right? Plus right? This is the same as this, okay? So now if we kind of rewrote this in the same way, it would be negative sine x. You can see that these are quite different, right? You're going to have a negative sine x value now adding to a negative sine 2x, whereas you were adding it to a positive sine 2x. So it's quite different, okay? And to verify that, when we go to graph them, so this graph here, this was sine x minus sine 2x, looks like that. And this one here was sine 2x minus sine x. Okay, so although the pattern kind of looks similar in a sense, it's quite a bit different. Okay, we can see from this one, zoom out a bit. Okay, this one dips down and then heads straight up. This one dips up and then heads down. Okay, so they look like reflections almost of each other, but they're not quite. They're a little different. Okay, so conjectures may vary. For example, know the order of the function matters. The graph should always be they're different. Okay. G. Investigate the sum of other types of functions. Use graphing technology to graph each set of functions and describe how the characteristics of the functions are related. So here we're given 4 different functions, 2 functions, and finally a third function, which is a combination of those functions. In each case, it's the sum. Okay. H says investigate the differences of each set of the functions in G by graphing the difference. So now they're subtracting y1 minus y2. So quite a bit of work here, right? We're going to skip to the results here and let's see. So G, the first one. So here's our equation, minus x and x squared. So this dark line here, that's y equals negative x. We should all recognize that. And then y equals x squared is this line here, which is a little bit lighter, but still darker than the lightest line. Okay, so finally the combination y3 of negative x plus x squared is this really light line. Okay, so negative x, x squared, negative x plus x squared. So what we notice is negative x, or the sum of the two functions, it's actually just a translation of the second function. Do you see that? The second function graphed y equals x squared is just translated 1 over and half down, looks like. Okay, so that's interesting. The negative x being added is just a translation, and that's because we can actually factor this out, right? We could factor an x out here, find our x-intercepts, and graph as well, okay? So what we notice is the first function is linear and the second is quadratic. The sum of the functions is the same quadratic, but the vertex is translated 1 unit to the right and half a unit down. Okay, so that's interesting pattern there when we combine a quadratic with a linear equation. At least the parent functions, we just had a translation of the quadratic function. All right, let's see what happens with the other one. So again, if you wanted to do these graphs by hand, what you would do is you would create a table of values. You would graph your x values and your y values for each function. And then to get the third function, you would just add the y values. Okay, so 2. Here's our equation now. We're looking at, let's put this up here. So there's our equation, root x and root x plus 2. And our final sum of equations is root x plus 2. So y1 looks like this, the darkest line. y2 is the lighter line, and we should be able to create those graphs just by looking at these functions, right? We're familiar with this parent function, and this is a translation of 2 units to the left. So we can see that those are these two functions. And finally, a combination of the functions, you're adding their y values. So this y value plus this, these two y values added will come up here, okay? This y value and this y value added will come up here, okay? And the x value for this and this is the same, right? So our y3 value looks like this. Okay? Why don't we have any values here for y3? Anybody know? If I just told you to get the y value of y3, you add the y values of y1 and y2 to get y3. Why don't we have any y3 values here? Because it should be the same as y2, right? If I'm just adding them, why not? Elijah.
Because y1 doesn't have any values.
No. It's okay, y values are undefined here. X values. What happens when we square root a negative number? Sorry?
It's undefined.
Right, it's undefined. So why is that a problem with y3? Okay, here's the equation for y3. Why do we have no y values when the x value is negative? Yeah, because this term here becomes undefined. And in any algebraic equation, if even one term is undefined, the whole term is undefined. Okay, does that make sense? Because I can't add an undefined value to a defined value. I can't say undefined plus 3 is equal to 3. It's not. So as soon as this value becomes undefined, the entire equation is undefined. Okay? So whereas y1 is undefined at any negative value, so you don't have any negative y values here for y1, the same is true for y3. Why? Because the y1 portion of the equation creates an undefined term. Okay? That's the reason why, if you're looking at the graph, you can't just take the y2 values, add them to 0 of the y1 values and say that's part of my y3 graph. It's not. All right, next one. So So we have an exponential function here, base of 2, exponent x. Our y2 is 2 to the exponent of negative x, and then our y3 is combining those values. So again, using the same logic, you graph y1 looks like this, y2 looks like this. At x equals 0, you're going to add these two values. So y1 is 2, y2 is 2, so you add them. Sorry, y1 is 1, y2 is 1, you add them, you get a value of 2. So to get this sum of graph, you just have to add these two values. Okay? You're going to add this really small value to this really high value. It's just going to go a bit higher. Okay? So here's our y1, here's our y2. Okay? So from these two exponential graphs, we actually end up with a parabolic graph, y3. Okay? And you can see all this when you combine the terms. If you factor them and rearrange them and simplify them, you can actually produce that quadratic algebraically as well. Okay? But it's important to note how they combine graphically to produce the third graph, or sum of difference graphs. Finally, the last one for the sum, we have cos x and cos 2x, and then we're adding them. So the dark line is just cos x here. The very dark line is cos x. The lighter line is cos 2x, so it has the same period, sorry, half the period, but the same amplitude. It's tough to see. Where is it? y2, oh, it's right here. So here's y1 going down and then up. Here's y2, down, up, down, up. Okay? And finally, when you combine them again, you're adding the y values. X values stay the same. Now we do the whole thing all over again, this time looking at the difference. We're just going to look at the graphs this time, okay? So the darker graph is the first one. The next lighter graph is the second one. And then the lightest graph here is the difference of these two graphs. Okay, so again, we notice with a linear and a quadratic, we end up with another quadratic that just has the vertex, the transformation of the vertex, and this time now there's also a reflection. Here we have the two exponential functions, and we get this function here. That looks almost like a cubic function, I would say. So in the difference of them. Here we have the other two functions, again looking the same, and now we have the new function where they're subtracted. Likewise with our sinusoidal functions, similar sort of idea. This time we have a very similar looking graph, except that again it's been reflected now in the x-axis. Okay. So is there anything that anybody has noticed in any sort of pattern so far? Doesn't look like there's any straightforward pattern. At least it's not glaringly obvious, right? Anybody? Do you guys agree? I don't see anything that's glaringly obvious. Okay, let's look at some of the conclusions and hopefully this will make... Let's see. How does the degree of the sum or difference of two polynomial functions compare with the degree of the individual functions? So, remember, what is the degree, first and foremost? Elijah's the only one, I think, that's awake. Anybody? The degree of a function, guys? Yeah.
Is it the exponent of the coefficient?
The exponent of the coefficient, no. So the exponent of the coefficient, what that means is if you had like this, that's the exponent of the coefficient, right? It's not that. Coefficients usually don't have exponents, right? Because they're usually whole numbers, right? The degree of a function. Kevin.
The highest exponent.
Yes, thank you. Right? Tell us that. Yeah, it's the highest exponent in the function. Yeah.
I was half right. For some reason, I thought it was the order.
Everybody's asleep, I think.
Get too tired.
Okay, how does the degree, the sum of the difference of two polynomials, compare to the degree of the individual function? All right, so the degree of the combinations of functions is less than or equal to the highest degree of the individual functions. Okay, so it'll never be more. It'll either be the same or it'll be less than. So when we combine these functions, y equals negative x and y equals x squared, the degree is either going to be squared or less, okay, of the combined function. Got it? All right.
Yes, sir.
J, how does the period of the sum or difference of two trigonometric functions compare with the periods of the individual function? Okay, it has the same period as the function with x and twice the period of the function with 2x. So we found that in the first example we did, right? That's pretty straightforward. Okay. When looking at the sum of two functions, does the phrase for each x add the corresponding y values together describe the result you observed for every pair of functions? Okay, this is right to the example we were talking about. What phrase would you use to describe finding the difference of two functions? So there's a problem with this function for those terms that were undefined, right? That was the only case where that didn't happen, right? But otherwise, for each x, you do add the corresponding y values together. So yes, for each x, subtract the corresponding y values. So when you're talking about the difference of functions, you subtract the y values. Sum of functions, you add the y values. Looking at the graphs of the two square root functions, explain why the domain of the graph of their sum is x. This is exactly what we talked about. Because the values of x less than 0, it's undefined. Okay? The square root of a negative number is undefined. And finally, the last reflecting question. Determine the y-intercept of y3, where y3 represents the difference of two exponential functions. What does this point represent with respect to y1 and y2? So the y-intercept of the y3 would be 0. This represents where y1 and y2 are equal and intersect each other. So when we have a difference of, say, this function and this function, if we have a difference, we subtract these y values because they're equal. The point on the difference of functions will be at 0. Okay? All right, let's look at a few examples. So we're given y equals, or f at x equals negative x squared plus 3 and g at x equals negative 2x. Determine the graphs of f at x plus g at x and f at x minus g at x. Discuss the characteristics of the resulting graphs. So again, the way to do it is you create a table of values, you plug in those x values, or in this case, x values for both functions, and then you just add them up. And then you can create the graph yourself. Okay? So x values are here, we add them up, negative 6 plus 6 is 0. And then here we subtract them. So this is the sum of functions, and this is the difference of functions. Okay? And then we take those and we graph them. The green is the sum of functions. Okay? And in this graph, the green is the difference of functions. Okay, algebraically, we can add them, factor, gather like terms, and then graph. Okay, so we can do it algebraically as well. Okay, so here is the sum. We're adding those two terms, factoring, putting into vertex form. All right, in vertex form, and then we can graph from there. Same thing for the difference of the functions here. All right, example 2, connecting the domains of the sum and difference of two functions. So if we have the domain and range of the difference of functions and the sum of functions. If f at x is 10 to the exponent of x, and g at x is log x plus 5. So the first thing we do is we sketch the graphs of f and g. So there's f and g, and we can determine the domain and range of those graphs by just looking at them here on the graph. Okay, and then from that we can determine the domain of the difference of functions and the sum of functions. So an intersection is a set that contains the elements that are common to both sets. The symbol for intersection is like a large N. This is the intersection of the domains of f and g. So XER, they intersect where XER, it's all real numbers, intersects XER where x is greater than -5. That's this value. And is equal to XER where x is greater than -5. Okay, number 3, modeling a situation using a sum of two functions. In the past, biologists have found that the function p at t is equal to 5,000 minus 1,000 cos pi over 6t models the deer population of Provincial Park, which undergoes a seasonal fluctuation. In this case, p at t is the size of the deer population. T is months after January. A disease in the wolf population has caused its population to decline, and the biologists have discovered that the deer population is increasing by 50 deer each month. Assuming that this pattern continues, determine the new function that will model the deer population over time and discuss its characteristics. So essentially the first step we want to do is graph this function. Okay, so we have this graph here. That's our average yearly population minus our seasonal variation. Okay, so we have a linear function minus a sinusoidal function. Okay, this is our new change now. Our average yearly population is increasing by 50 every month. So t, again, is our value of months. So we're going to add 50 every month. And we're minusing that same seasonal variation. So if we graph this new graph, we get something that looks like this, where the deer population is still fluctuating by month, depending on what month of the year, but it's on the continual increase. Okay? So this is kind of the first real-world scenario where we can see that there's quite a simple yet valuable result in combining two functions. Okay, example 4. Using graphing technology to explore the graphs of f minus g, where f at x equals x squared and g at x equals nx, or NEW. Discuss the results with respect to this type of function, its shape, its symmetry, zeros, maximum values, intervals of increase and decrease, and domain and range. So in this case, we're combining a quadratic and a linear function. And the linear function has different slope values. Okay? So our graphs end up looking like this. The series of parabolas that f minus g produce will have identical shapes since a is equal to 1. It appears that as n increases, the parabola is shifted to the right and down. So what's happening is, as the slope of the linear function is increased, the graph, the quadratic graph, gets moved to the right and down. And that's what we saw in the investigate. Most of these functions are neither odd nor even, and their graphs are not symmetrical about the origin or y-axis.